Thank you so much for the introduction, Tamara, and thank you everyone for being here, for coming this morning or this afternoon if you're in the UK. I'm Alba, I'm a PhD candidate at UC Davis, as Tamara said, and today I'm going to be sharing with you some of the work my collaborators and I have been doing over the past 3 years. And this title is a little bit misleading. I'm actually going to be giving a broader talk than this. I'm going to be taking you on an east to west tour of Southern California. We're going to begin looking at the damage zone of the 2019 Ridgecrest earthquakes. Then we're going to add some observations from prior events in the Eastern California shear zone and see how those compare to Ridgecrest. And last, we're going to move all the way west to where the San Andreas and the San Jacinto faults come together slightly north of LA. And we're going to talk a little bit about multifold earthquakes there and their frequency. Okay, so without further ado, I'm just going to start talking about damage zones right away. So many of us care about damage zones. They're a key component of the earthquake energy budget, seismic hazard assessment. They constitute a permanent sink of strain energy. They modify the elastic properties of the shallow crust, threaten lifelines, amplify ground shaking. There's just so many reasons geologists, geodesists, and geophysicists alike care about damage zones. But these different subfields of earthquake science all have slightly different definitions for what a damage zone is. So let's just quickly go over them. So geologically, we speak of damage zones as the fracture and warped volume surrounding a fault. Within this volume, fracture density decays away from a principal slip surface until it reaches some background level, as shown in this plot here from Mitchell and Faulkner. The same approach has been taken with aftershocks, where a damage zone is defined as the volume where seismicity decays until it reaches some sort of background level, shown here from the works of Power and Jordan 2010. Different functional fits have been used to describe this decay, but we typically favor things like exponentials or power law. So very sharp decay. Most of the knowledge we have of damage zones comes from strike slip faults. It's worth pointing that out. Okay, seismologically, damage zones are measured as a volume of decreased shear wave velocity that surrounds a fault. Sometimes this volume can also host guided waves. An example here from the work of Elizabeth Cochran. Red means slow shear wave velocity, cooler tones mean faster shear wave velocities, and you can see how those increase with distance away from the fault. Geodetically, damage zones have been characterized as areas of reduced rigidity, or for earthquakes that are directly imaged, the area where strain exceeds the elastic limit of the material. An example of that is shown here from Chelsea Scott's work, where the black lines outline the area, but bound the area where strain has exceeded the elastic limit of the material, which is shown in the yellow and blue colors. And a persisting question in damage zone studies has been whether there are breaks in scaling within the damage zone. This is very well exemplified by the work of Powers and Jordan in 2010. So I'm just going to quickly get my pen here so I can annotate this. Okay, so Powers and Jordan interpreted 3 zones from their decay and fracture in aftershock density with fault perpendicular distance. First, an area of sustained constant aftershock density that ends in a corner or a break in scaling that bounds an area where aftershock density decreases constantly until these aftershock densities meet some sort of background out here. And these plots inspire this idea of an inner damage zone that contains one or several strands of fault core, like shown in these cartoons. So this would be the inner damage zone. This would be the inner damage zone, which correlates with this flat area here. And that ends in a break in scaling. Some field geology studies have also supported this conceptual model of the damage zone. Okay. A challenge in damage zone studies is that the measurements of the extent of inelastic zones or damage zones are generated typically from a single data set, for example, a fracture or an aftershock distribution like I just showed you. And these data sets can capture an integrated history of the formation that spans multiple earthquake cycles and seismic processes, so they're not always comparable. The 2019 Ridgecrest earthquake sequence was so heavily monitored, and it provides this unprecedented view of the distribution of inelastic deformation from high-resolution imaging, geodetic data, and earthquake catalogs. So in our work, we integrate high-resolution maps of fractures, 2D strain maps, and aftershock catalogs to characterize the distribution of inelastic deformation around the faults that ruptured during the Ridgecrest earthquakes. So we incorporate 3 different rupture mapping data sets. The first one is the surface rupture map of Pony et al. 2020, which is generated from field and geodetic observations that are actually not shown in this plot. The second one is our OMAP of the surface rupture, which was generated from post-earthquake LiDAR data. That's what I'm showing you on the top left here. These north, can you see my pointer? Awesome, thank you. The north-south trending structure here is a rupture of the 7.1 main shock, and the perpendicular section to that is a rupture of the 6.4 foreshock. Okay, so this is our LiDAR map. You will note here that there are a few sections that are highlighted with orange rectangles. These are sections where the rupture was mapped from centimeter resolution aerial imagery. Some of this imagery was collected by NCOM at the same time from the same plane that was flying the LiDAR data. Some of this imagery was collected by EM peers with a UAV in the field. And at the bottom here is an example of what one of those sections looks like. This comes from this white star over there. And we're going to take a closer look at this in a second. So let's just move on and look at the right side of this plot. These are the epicenters of the aftershocks in the QTM earthquake catalog. And we're going to incorporate this catalog and the SCSN earthquake catalog for those of you that may be interested in the specific catalogs we used. Okay, I'm just zooming in into this section that I showed you earlier. This is the middle of the magnitude 6.4 rupture. And I just want to highlight how much detail this drone imagery allows. You can see that the rupture in this section, it's multi-stranded. In some sections, it goes blind and then it localizes again, goes distributed again. So there's so much behavior that we can see in even this like small snippet. I also want to point out to you that the volume surrounding the main fault strands is heavily fractured. They're discrete fractures that extend all the way to the edges of the footprint. This is just a nice field view of what's going on. You can see a large fault scarp in the middle here, and you can see all of this distributed fracturing extending away from it. And this is, let me move my pointer so I can play this video. Yeah, this is a view of a 3D view of the LiDAR point cloud. There are two faults in the middle here, and you can see these alternating pattern or fracture, a little mold, uplifted mold, fracture, uplifted mold. These are actually mold tracks in 3D, and it's really cool to see that the LiDAR penetrated into some of these fractures so we can actually see how they exist at depth. And I should note that this is vertically exaggerated 10 times. Okay, so going back to the data sets we're using, I told you we're using 3 different surface rupture mapping data sets. We're using 2 aftershock catalogs, and we're gonna supplement these data sets with the distribution of superficial strain mapped from satellite imagery cross-correlation. We use the fault parallel shear strains measured from profiles that are oriented perpendicular to the primary rupture and stacked over 138 meter distance along strike. You can see those stacked profiles here on the left. We find that inelastic strains, so something that exceeds 10 to the minus 3, are limited to 30 to 100 meters away from the fault. And beyond 1 kilometer, strains become too small to resolve from this approach. Okay, so now that we have all of our data sets, we're going to combine them, and we're interested in saying something about the distribution of inelastic deformation with distance away from the fault. And before I say anything, let's just quickly define what I mean every time I say inelastic. When I say inelastic, I mean that a point where the material has yielded. For the rupture maps and the aftershock catalogs, the mechanism for inelasticity is brittle fracture. The strain maps probably also capture some folding and block rotations that are contributing. Okay, so to investigate the distribution of inelastic deformation with distance away from the fault, we quantify the decay of fracture density, aftershock density, and strain intensity from stacked profiles across the rupture. We measure the nearest distance between each damaged feature and the main fault. We do this in 2D for the fractures and in 3D for the aftershocks. We fit this decay using the relationship from Powers and Jordan 2010, which is shown in the right side of the image here. Excuse me, where the decay is defined by the fracture density at the fault, V0, which is here, it's this intercept, a parameter defining the distance between the origin and unbreaking scaling, D, which is this point that bounds the flat part of the distribution, M, which is a parameter that defines the sharpness of the corner, of this corner D. We do hold M equals to 2 following the choice of Powers and Jordan 2010, though I will note that what M is doesn't really change the way the decay looks. And last, gamma, which describes the slope of that decay beyond point D. And I'm showing you what those look like for the aftershock data here. I'm going to add one more data set to this plot. These are the fractures. This is fracture density based on the surface raptor maps from the high resolution aerial imagery. Note that this corner D has moved inward a lot closer to the origin, but the slope of that gamma parameter, that the slope of the decay beyond point D, looks pretty similar to that of the aftershocks. Okay, I'm going to crowd this plot even more. Now we have all of the data sets I've mentioned stacked in this plot. The red line represents the decay in fracture density for the fractures mapped by Pony et al. 2020, which is based on field and geodetic data. The orange lines represent the decay in fracture density for the fractures mapped from the post-earthquake LiDAR data. And the gray line here, it's a bit hard to see in this plot, represents the decay in strain intensity measured from the second invariant of the finite strain tensor in those profiles I showed you earlier. So let's take a closer look at the parameters that define this decay. We're now looking at the distribution of the maximum likelihood values of gamma, which range from 0.9 to 1.4, and they overlap within uncertainty. We interpret the similar slopes, you can see this here, to indicate that fractures, aftershocks, and other processes captured by the strain maps are controlled by the same mechanism in stress fields. Okay, we're now going to take a look at the distribution of parameter D. Panel C shows the maximum likelihood values, or D, which is, as I mentioned earlier, this break in scaling, this end of the flat section of the curve. We also added the uncertainty in the fault location at the surface and at depth to the plots that is shown by the orange shading in the back. So I want you to note that the corner position D is farthest out for the aftershocks at 50 meters, and it sits between 0 and 12 meters for the higher resolution LiDAR field and image-derived fracture data sets, and it cannot be resolved at all for the strain data. So for these higher resolution data sets, these both on the order of the spatial error of the main rupture trace location, and also most of these feats allow for the absence of a corner. They allow for D to be equal to 0. And for the aftershock data, D is comparable to the 100 meter or so horizontal location uncertainty of events used to define subsurface fault geometry. So let's keep this in mind while we compare our decays to prior measurements of the extent of inelastic deformation from Ridgecrest. So here I'm showing you some of the work of Chris Milliner. Optical image correlation defines a 30 to 100 meter wide zone of inelastic strain that's centered in the rupture. So that's shown by these small gray bar here. You can only look at the x-axis here, and you can treat the width of that bar as like the width of the zone of inelasticity, right? So it goes from 30 to about 100 meters. And this map view here is showing you what that strain looks like. You can see that strain is very localized in these thin areas and then decreases quickly with distance away from the fault. Other studies of image correlation, this is the work of Selene and Tuan, have defined a broader zone that includes both contributions from elastic and inelastic deformation. So these are broad zones of deformation receiving both elastic and inelastic strain. And these zones are 600 meters to 2 kilometers wide. In the plot on the right here, you can see what those zones look like for the main shock. The length of each line represents the width of that zone as mapped in their work. Okay, and adding another set of data here, I'm showing you the extent of low velocity zones and trapped wave zones as constrained from nodal arrays that were deployed following the earthquake. So you can see the locations of these nodal arrays on the plot on the right here. It's a bit hard to see here, but the small red lines in the middle represent the width of the zones of trapped waves, and the small green sections that represent areas where the shear wave velocity was low, but it didn't focus trapped waves. Okay. And I want you to note that none of these width extents overlaps with the parameter D that we were fitting from our data. So based on the absence, or based on the overlap between D and uncertainty, and based on the absence of overlap between D and the extent of inelasticity from from prior data sets, we propose that D is actually an artifact of data resolution, and it's not a physically meaningful parameter. Our data instead suggests that damage zones manifest in this continuum of decay and deformation intensity. So this warrants caution in the use of a single data set for determining the effective edge of damage zones in numerical models and how we treat this in probabilistic displacement hazard analysis. And I guess another thing that's worth pointing out here is that all of these different data sets are just responding to different deformation intensities. So all of these gray and green bars that we're showing at the bottom coexist within the broader continuum that we are defining with these long wavelength decays that we're mapping from the high resolution raptor maps. Something else worth pointing out is that we've said that the overlap between gamma suggests that all of these inelasticity is representing the same mechanism and stress field, but it's worth pointing out that this is not something, we cannot distinguish between static or dynamic processes contributing to the triggering just from this decay exponent alone. Okay, so the next thing we want to do is we want to investigate the sensitivity of these damaged decays to lithology. So to do that, we filter through fractures cutting sediment or bedrock. It's important to note that, as you can see on our map on the left in A, that the bedrock area we sample is really, really small. So we have very limited data. But with that aside, we find that fracture density in sediment, it's typically 1.5 to 4 times higher than that of bedrock at a given distance from the fault. And the decays are actually quite comparable. Again, the reduced fracture density in bedrock may reflect the greater cohesion of that material versus sediment. But we still think that the similar decay exponents support that the mechanism responsible for the nucleation of fractures operates under the same stress conditions irrespective of material. Okay, the next thing we're interested in doing is evaluating along strike variability and assessing the sensitivity of the damage zone to unfold slip. So to do that, we compute this decrease in fracture density with fault perpendicular distance and the average invariance of slip in the sections that we map from the high resolution imagery, which you can see in panel A here. So we have the slip invariance of that slip for each of these sections, and their respective fracture density decays on the right. And you can see here that there's not really a correlation between the overall fracture density and slip magnitude. There is variability in fracture density, right, and that intercept, but that actually doesn't correlate. The high fracture density area doesn't correlate with the area of the highest slip. So overall, we find that there's no correlation neither between the shape of the plots or the absolute fracture density and slip or slip variability. And I should note that this is for slip at the surface only, though. Okay, the next thing we want to do is we want to directly compare our fracture maps to strain maps. So here we're looking at the magnitude of strain conveyed by the second invariant of the strain tensor, which is shown on the left plots. And on the right, we have a fracture density from the high resolution UAV mapping. And overall, we can see that to first order areas of high fracture density and high strain overlap. We can see this like area of hot strain thinning and widening similarly to how the fracture density is doing. But I want to point out to you some areas of disconnected high fracture density that do not necessarily appear on the strain maps. And I think this warrants caution when we're thinking of probabilistic displacement hazard analysis and where our surface displacements are. There are areas of fracturing that are just not resolvable from the strain maps. So I think these highlight the value of high resolution orthophotography in identifying individual fractures. Okay. And I also think this provides a potential explanation for why inelastic deformation is rarely mapped beyond the main raptor when we're relying on cross-correlated satellite imagery. And I suppose because this is a geodesy consortium, I should mention that all of this satellite imagery is from Spot 6 satellites. Okay, so far we've taken this damage zone model, we've described a damage distribution based on different data sets. And now what we want to do is see if we can take these damage distributions and say something about the physical properties of the damage zone. Okay, so on the right here, on the left here, I have the density decays from the imagery data, fracture density decays from the imagery data, which is our highest resolution data set, and that's the most reliable decay. And what we want to do is, based on the relationship between fracture density and shear rigidity, we want to estimate how much this fracturing contributed to rigidity decrease in the volume of rock that's surrounding the Ridgecrest faults. To do this, we rely on the seminal work of Budiansky and O'Connell in the 70s. And doing this requires integrating both the density and the length distribution of mapped fractures. And sparing you all of the details, here we arrive to the plot on the right. Based on this analysis, we predict a decrease in shear modulus by 40% immediately adjacent to the fault and sediment. I guess I should mention that G damage over G is the ratio of the shear modulus of the damaged material versus the undamaged material. So you can think of this as a percentage. So about 40% decrease in sediment immediately adjacent to the fault and about 20% in bedrock, declining to less than 1% at 100 meters away. And I should note that these estimates are within the rigidity decrease range that was geodetically estimated for secondary damage zones by Eric Xu, also in the Ridgecrest area. Okay, so another way to think of this is, remember when I showed you earlier, these low velocity zones measure a depth that sort of have this tractor, they decrease with distance away from the fault. Our estimates for Ridgecrest are based on the fracture density mapped at the surface, but we do know that the width of reduced rigidity we predict compares pretty well to the width and velocity structure of trapped wave zones that were observed post-seismically. These zones are very variable in intensity along strike, but they typically extend 3 to 5 kilometers down dip and they remain constant in width. Okay. Something else I want to point out to you is that our analysis shows that low levels of rigidity reduction may be expected far from the surface rupture trace, right? We have all of these low intensity inelasticity that exists pretty far away from the fault. And this finding is supported by regional reductions in shear wave velocity following the Ridgecrest earthquakes. These are measurements from the very far field. They average through a large crustal volume surrounding the fault, and they show this ubiquitous, though small, around 2% velocity reduction, which we think may be akin to the widespread damage we're mapping at the surface. So our observations simultaneously reveal two things. One, the role of macroscopic fracturing in generating these intense near-fault damage, which the shear modulus decrease plot captures really well, but also the widespread damage may accumulate regionally. And what I really want to point out to you is that both of these behaviors, both this high intensity near field and widespread low intensity damage, are part of the same continuum. They're happening as part of the same nonlinear fracture density decay. Damage zones are heterogeneous. We all know that. We've seen this from field observations. The seismological constraints on low velocity zones from Ridgecrest show these zones that are quite variable along strike. Fractures occur in clusters in our maps. And this makes it challenging to treat damage zones in model. But within this heterogeneity, there are simple relationships that describe the average intensity of deformation, such as these, that may be useful to develop generalized models of all damage zones. Okay, and now I've been entertaining you for 26 minutes, and I want to instead start asking you questions. I want you to help me answer these questions that I think this work raises. So first question is, how much of the damage we map is inherited? How much of that 40% shear modulus decrease is just reactivating cracks that were already there, contributed from prior earthquakes? Similarly, how much of the damage is recovered or healed after the earthquake? How much of these 40% is going to be 10% a few days after? And I think in a more long-term thinking, what happens to the crust in zones of dense faulting, such as the Eastern California shear zone? We know that some of the damage we map has to be permanent because we see damage zones existing along faults in late interseismic stages. For example, on the Calico fault, which is also pretty close to Ridgecrest here in the Eastern California shear zone. So we have these areas that are like 20 kilometers from Ridgecrest that are receiving some like low intensity damage from that event. But that same area, it's 10 kilometers away from the Garlock, it's 5 kilometers away from the next fault over. So what happens to these zones that are receiving damage from multiple sources in the long term? How does this widely low intensity damage volume that's permanently deformed evolve? What does that mean for the evolving properties of the crust in a place like the Eastern California shear zone? What does that mean for permeability? I think all of these are open questions. Another question that this work raises is whether Ridgecrest is an exception. We all know Ridgecrest is kind of weird. We have these orthogonal faults. We have cracks everywhere. So we took a look at other well-documented either Eastern California shear zone earthquakes to see if they look any similar. So when we look at the fracture density decay for these events, the slopes overlap pretty well with our Ridgecrest data, particularly with the Ridgecrest imagery. So we see these remarkably similar full perpendicular fracture density decays and also widespread damage. And something that all of these events have in common is that they are multi-fault earthquakes. All of them involved several individual faults that ruptured together. These events are tricky. They're hard to identify in the paleoseismic record. They're hard to correlate across faults. They alter the stress and probability of events throughout a fault system. So they're really hard to deal with in long-term simulators. So we're really interested in what are their mechanics and how frequently they're happening. These Eastern California shear zone events happened in pretty remote areas, which is good. But fault junctions with the possibility of making multi-fault earthquakes do not always occur in isolation in remote areas. Furthermore, all of these events occurred in slowly slipping faults that do not have good paleoseismic records available. So can we have a better natural laboratory that's both more important for hazard, threatens more of a population, and happens along faults that are better documented? Yes, we're going to move west to the San Andreas and San Jacinto faults, which come together. This is where Ridgecrest is in this corner. These are the San Andreas and the San Jacinto highlighted in red. And they come together here at this place called Cajon Pass, which is just slightly north of LA. These faults carry the majority of the Pacific North America plate motion. They're sleeping much faster than the Eastern California shear zone faults we were just looking at. California has this short historic record, but it has a really long paleoseismic record. Within this short historic record, there's the 1812 event, which is this enigmatic event. It's been proposed to have ruptured both on the San Andreas and the San Jacinto fault. It was pretty compellingly shown in the work of Julian Lossos that it is dynamically possible to have the earthquake jump between the two faults, but this is not clear in the geologic record. And the reason for that is that Cajon Pass is a very challenging geomorphic setting for paleoseismology. The northern San Jacinto, it's aligned with major river canyons, shown here. The San Jacinto is somewhere in here. It's really hard to map. It's really hard to measure slip. These streams are carrying huge boulders. It's not like you can dig a trench and date things. So understanding what earthquakes do at Cajon Pass is pretty complicated. This is made worse because the northernmost paleoseismic site on the San Jacinto fault, shown here, the Colton site, is 30 kilometers away from Cajon Pass. So you could stick a full magnitude 6 event in there and not have a paleoseismic record that reflects it. So on this map here, I'm showing you the paleoseismic sites along the San Andreas and the San Jacinto faults. Each of those black dots is one of them. And I want to bring your attention to this LCRF sign here, shown right in the middle here. The LCRF, or Lytle Creek Ridge Fault, is a newly discovered low-angle, shallow normal fault sitting right at Cajon Pass. It is too shallow, it is too short to be seismogenic or act as a transverse structure, but we think it's ideally positioned as a passive recorder of linked rupture. So what I'm going to try to convince you next is that we can use these small faults that are strategically positioned to understand what the big players are doing at complex places like Cajon Pass. Okay, so let's get to know these Lytle Creek Ridge faults, which I'm just going to go ahead and say LCRF for the rest of the talk a little bit better. Here I am showing you the LCRF cutting through the Pelona schist. The fault is right here. Okay, this is getting ahead of myself. This is a paleoseismic trend we're going to be talking for the rest of this talk, is in location 2 here, where there's a bunch of ponded sediment against the scarp. And 3 here, I'm showing you a little bit of a bedrock exposure of the fault cutting through serpentine. So let's talk a little bit about why this fault is well positioned to be a passive recorder of joint rupture. Like I said, it's too shallow and too short to be seismogenic on its own. The LCRF, it's a normal fault that is sitting in the transverse ranges, which is an area of regional strong north-south contraction. So to overcome that, we need really strong local dilation. So to consider how we're going to make that strong local dilation, we built a set of Coulomb models where we place slip on the neighboring part of the San Andreas and the San Jacinto, where slip is tapered to simulate a stress drop of approximately 6 MPa. And we supplement these models by quasi-static slip models to understand the magnitude of trigger slip. So I'm going to go through 3 different rupture scenarios. What you're going to see here is the geometry of the faults. Faults that are highlighted in orange are rupturing. This is the slip imposed on the LCRF. This is the stress imposed on the LCRF by the rupture on the other fault, whatever fault is in orange. And this is the slip vector imposed on the LCRF. So rupture that terminates on the San Andreas without stepping over induces a strong component of left lateral slip, more than normal slip on the LCRF, which is not consistent with this normal fault that we observe in the field. Okay. If we impose slip only on the San Jacinto fault, we get the right slip vector, we get normal slip, but we impose too little displacement. It would not be distinguishable from our paleoseismic record. So different slip conditions like larger slips, steeper slip tapers on the San Jacinto may be able to trigger larger slip on the LCRF. It seems likely that we'll get an increase that's large enough to match what we're going to see in the trench next. Okay, and here's the third scenario involving taper slip on both the San Andreas fault and the San Jacinto fault. This triggers double the stress change on the LCRF than the scenario that involves the San Jacinto fault alone, and it triggers slip on the centimeter range. So what we hypothesize here is that the LCRF is most likely to host the large slip measured in the trench, which we're going to see in a second, when both the San Andreas and the San Jacinto fault are rupturing together. It doesn't mean that it's insensitive to what's happening on the San Jacinto when it ruptures alone, or even the San Andreas when it ruptures alone, but it means that we are unlikely to find it in our trench record. Okay, so as I said, we dug a trench, and I really want to emphasize here that this trench was dug by hand. We hiked to the San Gabriel Mountains and we spent 7 days digging an extremely large hole that's 18 meters long. It's 1 to 3 meters deep and about 1 meter wide. And we started digging way too far back. So we had to dig for a lot longer than we should have because it took us forever to actually find the fault. But here is the fruit of our labor. This is our trench log. And we found in our trench 3 events. These events are highlighted in yellow here. So the event horizons, the capping horizons are shown in yellow. And we have this distributed fault system with a principal splay. At the bottom of the trench, we were able to find the master fault that exposes the Polonus schist. So 3 events. And we built a chronology from radiocarbon ages from charcoal samples in the trench. We use a Bayesian model built with the Oxcal program that includes stratigraphic order. It includes several charcoal ages per unit, event horizons, and we also include historical data in the form of invasive pollen, which we're going to get to in a second. So, this should be named events 1, 2, and 3, not events 1, 3, and 4. Sorry. Okay, so event 3 at the bottom here, you can see both event 3 and event 2 have pretty large probability density. And I want to bring your attention to the most recent section of the paleoseismic record. We are interested in knowing whether the most recent event, which is historical, is the 1812 event that I mentioned earlier has been proposed to be a multifold earthquake, or the 1857 event, which is well documented on the San Andreas fault, but not hypothesized to have involved the San Jacinto fault. And we can refine these ages for the top part of our trench by adding constraints from invasive pollen species, which their introduction dates are well known in California. So we found 3 interesting invasive pollen species present on the most recent record of our trench. These are tamarisk, Spanish broom, and Russian thistle. And I will note the tamarisk and Spanish broom, which were introduced in 1839 and 1848 respectively, are on the unfaulted unit that's on top of event 1. Thus, this helped us rule out 1857 as the most recent event. It has to be 1812. Okay, so let's put the chronology from the LCRF in the weather context of the San Andreas and the San Jacinto fault paleoseismic chronologies. Based on the number of events and the time interval that's covered in a trench sediment, we can estimate a recurrence interval. That's about 660 years. So 3 events in 2,000 years. Okay, if we assume that the record in the trench contains large events that represent joint rupture with the San Andreas and the San Jacinto faults, and I guess I should have pointed out in the trench that each of these events has like around 50 centimeters of slip. So we're looking at large events here. We can compare the number of events in our paleoseismic site at the LCRF with those at paleoseismic sites north and south of Cajon Pass in the San Andreas and the San Jacinto faults, and we can compare the numbers. It's worth pointing out here that we cannot pinpoint specific events. Each of these PDFs represents a single event, but they are too broad on the LCRF to be individually correlated to events on the San Andreas and the San Jacinto. However, we can get an understanding of the frequency of linked events if we compare the total number on each. Okay, so I've counted all of the PDFs in each of these. And from this, we find that around 3 of 15 for the San Andreas and 3 of 13 for the San Jacinto events are shared respectively between the San Jacinto and the San Andreas and are recorded in the LCRF. So hopefully by now I've somewhat convinced you that the LCRF is a good recorder that gives us an insight into the timing of events that bridge the earthquake gate. And now I'm going to try to convince you that it also gives us some key insights into rupture behavior of an earthquake as it approaches the step over. So we use this finite element mesh that includes the geometry of the San Andreas and the San Jacinto faults. This is the USGS geometry, and this is the mesh that Julian Losses made for his 2016 paper. And we've added the LCRF here based on the geometry that we measured in the field. Okay, I've exploded a view of that mesh with the 3 faults here. So we have the San Andreas fault with all of its paleoseismic sites. We have the San Jacinto fault with all of its paleoseismic sites, and we have the LCRF in the middle. And to better understand what events trigger slip on the LCRF, we're going to use the 1812 and the 1857 earthquakes. We use these 2 earthquakes because there are prior slip distributions that are available from other studies and our chronology and slip measurements from the trench. So for the 1812 earthquake, I'm going to use the work of Losses 2016, his final slip from his preferred model, which matches slip on paleoseismic sites, which is why he preferred that one. And then for 1857, I'm going to use the work of C and Zilke, which are slightly different, and we're going to discuss how those records are different. Okay, so starting with, starting with 1812. Okay, this plot is a little bit complicated, but on the y-axis, I have a lateral slip, right lateral slip. On the x-axis, I have distance along the mesh. And both folds are on the same x-axis. In green, I have the distribution of the slip on the San Andreas fault. The location of the LCRF is shown in red. And in blue, I have the distribution of slip on the San Jacinto fault up to Colton, which was the northernmost paleoseismic site on the San Jacinto. So we're 30 kilometers away from the LCRF. And here I'm using the slip distributions from Julian Loss's preferred model. So we have all of the distributions with the paleoseismic sites where the slip distributions match what was observed in the field. Okay. So, just added those sites. And now we are going to see what happens in this northern San Jacinto fault. So what I'm going to do here is I'm going to test different slip distributions on the northern San Jacinto and see how much slip they trigger on the LCRF. And this is a simple friction model where fault slip happens when the static friction is overcome. So let's begin. Here's one example. This is actually starting with the losses 2016 slip on that area. And the white line here is slip on the San Jacinto fault, but it is color-coded by the amount of slip it triggers on the LCRF, the amount of normal slip it triggers on our little fault here. Notice the scale is logged and it's in centimeters, not in meters. We do that many times. And we find that the models that impose slip that's comparable to the trend, so something that exceeds 10 centimeters scale, have in common two things. The first one is that they carry high slip north of the Colton site and they taper steeply, losing about 1 meter of slip per kilometer of fault length. And this is consistent with slip tapers in raptors that breach stepovers, which was shown previously in the work of Chris Schultz and the work of Austin Elliott. We're gonna put another way to visualize this data back here on the exploded fault view. You can see on the San Jacinto fault that the model slip, this is model slip from the losses paper, up to Colton. Slip distribution from losses up to Colton, and then our model slip on the left side here. This is what our preferred model looks like. Overall, we find that raptors that trigger slip on the LCRF comparable to that in the trench have to exceed 5 meters of slip on the northern San Jacinto and have to taper really steeply. That is a lot of slip, so there's a good chance that there are multifold raptors that our record doesn't hold. So we treat our LCRF record as a minimum amount of joint raptors in the past 2,000 years. Okay, but can the 1857 event be on the LCRF? We've argued that's not the case based on our pollen data, but just let's take a look at what the 1857 event on the San Andreas would do to the LCRF. First, we try the slip distributions from C1978, which placed the earthquake ending before the Cajon Creek paleoseismic site up here. I will note that we also allow the San Jacinto fault to allow it to slip in response to the slip on the San Andreas. But the color bar is the same as that in the San Andreas. The slip distribution on the San Andreas does nothing to the LCRF, really, and it does nothing to the San Jacinto fault. But there is more data for the 1857 event. So here we are placing the slip distributions from the Zielke et al. 2012 paper. This distribution carries the event farther south than the seed work beyond Pittman Canyon. They have several measurements and they're ranked based on how high fidelity they are. We only use the high fidelity slip measurements in the paper. The slip distribution imposes about 10 centimeters of slip on the LCRF. So looking at these model results, the 1812 events is still the strongest candidate. But again, this doesn't mean that we can have slip on the LCRF from raptors on the San Andreas only and some slip on the San Jacinto. But again, because the slip we observe in the trench is so large, it is unlikely that the 1857 event is there. Further supported by that pollen data that showed us that it's likely to be 1812. So to wrap up this part of the talk, San Andreas and the San Jacinto faults have ruptured together at least 3 times in the past 2,000 years. The LCRF ruptures passively with a recurrence interval of about 660 years, and about 20% and 23% of the ruptures that are paleoseismically recorded on the San Andreas and the San Jacinto faults are shared between the two of them. Last, to activate the LCRF with slip in the centimeter scale, slip on the San Jacinto fault must taper steeply and halt abruptly about 3 kilometers northwest of the LCRF, and we require high slip on the northern San Jacinto to trigger the amount of slip we observed in the trench. So with this, I'll just take any questions, and again, thank my collaborators one more time.
Wonderful. Thank you so much, Alba. That was a really interesting talk and great to hear so much of your work. If you have any questions from the audience, please do put them in the chat or the Q&A box, and we can get through them. I did write one question out, and it's quite a way back in your talk. I was wondering, when you're talking about the variables of the density of fracturing, and you talk through sort of the surface geology, and I can't recall the other variable that I was thinking of.
Slip.
Slip, that's right. Yeah, slip. Are there any other variables that you considered or that you think could be considered in that sort of thing? I'm thinking things like the strike of the fault or the strike of the stress around the fault or things like that. Like, is there anything else that you think should be considered there?
Yeah, so I guess our way around strike here is that we're always looking at fault perpendicular profiles, right? But yeah, strike could influence, right? I've also thought about areas that are in compression versus areas that are in tension. The expectation is that fracture density should be different for those. We're averaging over fairly large areas, so all of that's going to be smoothed out, but it is likely that there is variability due to those factors. Another thing I've thought about a lot is we compared our measurements to slip at the surface, and we didn't find a correlation there, but I wonder if we were looking at the shallow slip deficit, if we were looking at the magnitude of slip integrated over a larger area, if we would be more likely to find a correlation doing that.
Yeah, okay. I guess, yeah, the only way to get it slip further down or like fracture density is not going to, we're never really going to get to that any further down, right? Cool.
Aftershock density gets you somewhere, but yeah.
Yeah. Okay. We have one question come in. I have to apologize in advance for my pronunciation. Xingchu Shu says, "Nice talk, Alba. I'll have to leave early for another meeting. See you soon." As I say, sorry, I didn't actually read that.
Thank you.
I did read that comment before I read it out. Thank you. I also had a question come in from my co-host. We do have another question, but I wanted to ask this very quickly because it's an easy answer. My co-host Scott asked me during the talk, do you know how she measured or mapped out so many of the fractures? And I know the answer, but you want to?
Yes. So the fracture maps, which I quickly had like a little note there that said like the paper went from being Nature Geoscience to being SRL, because we have an SRL paper that has just the high resolution maps published alone. And this was a big team effort conducted in summer 2021. It involved 5 SCEC inters that were employed full-time, mapping each of those regions. And then I mapped 2 of the regions as well. And then a UC Davis student also helped us. So this was a team of 6 mappers devoting to getting all of these tiny cracks in the map.
Such an incredible effort. Okay, Scott. That's what we do when we get high resolution imagery. We just go crazy. Cool. I'll read out some of these questions that are coming in. So Alex Hayton has said, "Thank you, Alba. Great seminar. 2 questions. This is in the Q&A box, by the way, Alba. 2 questions. Part 1 of your talk seems to show that field or remote sensing offsets, surface slip, tells a different story of damage zone than aftershocks, guided waves, strain from optical image correlation, etc., which is slip at depth. Does your work show a decoupling of surface and deeper expressions of damage zone?" I might let you answer that before I ask the second question.
So I think that the aftershocks, the strain, and the fracture maps are actually showing the same story, and the variability within that story is it has to do with differences in the resolutions of these data sets, and it's not actually like a physically meaningful different thing that's happening at the surface versus at depth. I should point out here that the aftershocks I was comparing to in those plots are only shallower than 5 kilometers. So I think the story of what we see at the surface here holds down to 3 to 5 kilometers. It holds down to where we see those seismologically measured low velocity zones. I'm not going to say anything deeper than that. But no, I think that at least to that depth, we are seeing a coupling of what's happening at the surface and at depth. And then how does the LCRF record align with the maximum raptor model for, yes, so it aligns pretty well. Our frequency is comparable to that in the Shear and Yule model. And also our frequency is comparable to what's predicted by user 3, in case you're curious about that too.
Cool. Thank you so much. If you have any follow-ups, Alex, please feel free to put them in the chat. I'm going to ask a question now from Massimiliano Poreccia. Which is the effect of lithology and their physical properties, e.g. stiffness, on the density fracture?
So what we see is a fracture density in bedrock is 1.5 to 4 times lower than that in sediment. Again, we sample very little bedrock area, so it's hard to tell. I guess, and we have attributed this difference to cohesion, but I guess stiffness of the materials may also play a role. We do not, the sediment here, we're treating sediment in a lump here. We're lumping it all together, but sediment is quite variable throughout the raptor, right? There are sections that look like this salty crust thing that's behind me. There are sections that look sandier. We haven't really looked at whether there are differences between those segments. I know the USGS, sorry, not the USGS, the California Geological Survey is working on a map from the high resolution imagery that spans the whole raptor as opposed to our 5 different sections that we looked at. So I think once that map is available, we're going to be able to tap into these questions. We're going to be able to generate those fracture density decays for much larger areas. So I think this is something to keep in mind for when that data becomes available.
Cool, thank you so much. There's also a question here from Andrew Barber. It says, hi Alba, great talk. With Ridgecrest, are you able to separate fractures generated from the magnitude 6.4 foreshock? If not, how do you think that contributes to the decay pattern?
Mm-hmm. So here we mixed everything together, and our criteria was that the fracture was linked, the parent fault of the fracture was whatever the nearest fault was. That obviously gets pretty tricky when you get to the intersection between the main shock and the foreshock, but that's the criteria we held. People have shown before that these fracture density decays get more gentle when you have multiple faults. So in areas where the main shock and the foreshock are intercepting, I suppose that we would find slightly more gentle slopes if we were to sample those areas independently. I don't know if that quite answers your question, but I think that's what it would do to the decay pattern overall.
Cool, thanks so much. If you have any follow-up, Andrews, please feel free to put them in chat. Elise Godre has asked, I have a question about the last part of the seminar. How might a compliant damage zone on the larger faults affect your modeling results?
That's a great question. I don't know. Here we try to keep things very, very, very simple. We just wanted a first order constraint on what makes the LCRF slip. I know that people have worked on simulating things like bimaterial interfaces and seeing how that influences raptor linkage between the San Andreas and the San Jacinto folds. What people find when they put those bimaterial interfaces, which I guess it's akin to having a damage zone around the San Andreas fold, or at least like showing a contrast between materials as you cross the fold, is they find that there is a raptor direction that's preferred. We cannot use the LCRF to say anything about that though.
Cool, thank you. I had a quick question as a follow-up that just occurred to me. With the LCRF, I forget what the geomorphology around the trench was, but do you expect that you could have had sort of tens of centimeters of slip that had been removed from previous, like do you think that they could have been removed and not preserved in the trench?
So the trench record is fairly continuous. It's a combination of debris flow deposits and then soil horizons that form. So, and when we look at the ages of the trench, it's pretty continuous. So I don't think we have big time intervals that are missing. I think that the thing that's most likely to cause events to be missing on the LCRF record is if the mechanical conditions are not favorable for the LCRF to be triggered, but favorable enough for both faults to fracture together.
Okay, right. Has that been modeled sort of, or did you consider modeling that? Rupture of the two big faults, but not the little one.
Oh, that's been extensively done, mostly by Julian Losses, but Yehuda Ben Zion's group has also tapped into that work. So yeah, I guess what we were trying to do here is we had all of these robust modeling work that was suggesting that these faults could rupture together, but we didn't have a geological record to show that these faults do in fact rupture together.
Yeah, cool. Thank you so much. Okay, so there's no other outstanding questions. If you have a late question, get it in the next 20 seconds or so. But we're right on the hour. So in, for the sake of everyone getting to work or getting to their dinners, depending on what time zone you're in, or breakfast even, who knows. I think I'll call it there. And thank you so much, Alba. It was a wonderful talk. Thank you so much for taking the time to put it together for us.
Thanks for having me, and thanks for attending.